Okay, great. So my project is an industry-led project. I'm working together with this company, Agilent, who have this device called an ELSD. And it is a chemical analytical instrument used in industry to detect compounds. It's used in the pharmaceutical industry and in the food industry. And it's used fairly widely, but the actual understanding of the physics behind the device isn't properly settled, and there isn't a final sort of working model as to how it works. So my job is basically to fill that gap, to actually understand the physics underlying the device. So the idea of the PhD is basically make a zero-dimensional model, validate that with experiments, and then once we know how the physics actually works, that can lead to actual optimization of the product. This is interesting from an aerosol point of view because you actually aerosolize your sample through this, and it requires understanding of the physics through the understanding of the gas flow, the evaporation of the aerosol, and then the detection of the aerosol by light scattering at the end. So the idea through this project is to make a series of different models, all of which will link to each other. So you'd link the output of one model into the next one, so that overall you can actually have an overwide sort of system transfer function that will tell you, given some inputs, what do you expect as a simulated response to actually come out. This is the actual device, and this is what it does. So the ELSD detects analytes. What it does is you have a separator column, like an HPLC, and then you have one solvent with one solute inside of it. That gets atomized, and then you form this aerosol. The aerosol is passed through a heated tube. The heated tube takes all the solvent away, ideally. It dries everything out, so that you end up with dried particles. The dried particles then pass in front of a light source, and then they get detected by laser. Everything about this changes depending on any one factor that you change. So if you change your solute, you're going to get a different result. If you change your solvent, different result, different flow rate, different relative humidity, different composition. So in terms of actually getting through with this, it's necessary to sort of break down each stage, understand each stage at a time, and then put it all back together at the end. This is what the machine actually looks like. The atomizer sits here in number one. Then it can split the excess droplets, the stuff that basically collides because it's too big, gets taken out through particle impingement and goes into this reservoir that has a P-trap. This P-trap is filled with liquid, so no gas escapes. The gas is forced through here. This is actually another gas injector. So this is some secondary drying gas that really lowers the RH down to promote drying. The particles then pass in front of the detector. There's another gas source here. It's actually an annular focusing gas that drives the particles towards the center of the tube. And then they get detected and passed out through the exhaust. This is also blocked out. So knowing this, the first stage is atomization. This is actually, oh, you can quite see because of the thing. Anyway, and just underneath there is the actual atomizer that's used. So it's a twin fluid concentric nebulizer. You basically have this capillary tube that carries liquid through, and then you have an annulus of gas around it, and a meter, a nozzle, and you form a droplet distribution. The way that this particular atomizer forms droplets is through two processes, instabilities that grow, that then form droplets out of it. The first instability is a Kelvin-Helmholtz instability that I depicted in this graph here. Basically, ligaments, fingers, grow via Kelvin-Helmholtz instabilities when there is a velocity shear between two fluids of two different densities. These fingers are then formed, and you have to bear in mind that the gas is still colliding in this direction, and all of a sudden, there's going to be fluids pushing with different weights. This causes Rayleigh-Taylor instabilities to form, and the combination of these two instabilities, I've put the wavelengths of them here, for example, will cause droplets to form after that. Knowing this, I wanted to actually characterize what was going on, so I did some PDPA experiments. PDPA stands for Phase Doppler Particle Analyzer, and it's basically a way to measure droplets in situ using light scattering. I characterize this atomizer by moving the probe volume around radially along the nozzle, and I tried a bunch of different values, different flow rates, liquid flow rates, and so on. And I got these sorts of results. So in terms of droplet distribution that's initial, basically just straight out of the nozzle, I got this sort of droplet distribution with a mode of about 10 microns, mean diameter of 10 microns, and a sortie mean diameter of 27. It was very polydisperse. This was taken basically at the closest possible value that I could with this instrument next to the nozzle, which is 3 centimeters in height. After playing around with it, you could tell that it responded as we expected. If you changed the gas flow rate, if you increased the gas flow rate and left the liquid flow rate at the same rate, the droplets would get smaller, as represented here. So this would be with the gas flow rate having smaller value. If you increase the gas flow rate, the droplets get smaller. If you do the other way around and you keep the gas flow rate the same and you decrease the liquid flow rate, then you also find that you decrease the droplet sizes as expected. And in terms of counts and where they're located as expected, you have the highest concentration of droplets near the nozzle, and you get this cone shape that actually comes out of it. Once we have one droplet distribution, there are certain colorations that you can use to map that onto other different solutes and solvents that you can use. So for example, we've done it with water, but you might get a different droplet distribution if you use something with a different viscosity and surface tension. It might change the diameters that you might expect. This correlation makes that jump. So by doing enough experiments, you can get these constants out, and all of a sudden you can actually plot and get different mean distributions that you can make log normal distributions out of if you plug in new property values, such as having a new Weber number, which depends on the surface tension of your material, Reynolds number, which depends on the viscosity of the gas, you can change that, and so on, and the liquid density, which you can change as well. So by just changing these numbers, you can generalize this equation to have any droplet distribution that you want. In terms of the next stage, it would be particle impingement. I modeled this basically with the Stokes number, which is a non-dimensional number that tells you whether or not a particle is going to follow the flow. If it's a Stokes number larger than 1, then it doesn't follow the flow. I'm assuming that means it crashes. So I'm talking about this Y junction just here after the atomizer. If the Stokes number is less than 1, then I'm assuming it follows the flow and it carries on through to the detector. I apply this with some other equations that can be found in the very good book by Hines, and you can get a cutoff diameter that allows for a new particle distribution after impingement to be carried on through. In terms of evaporation, it was fairly straightforward. I used an evaporation model based on the equations of Abreu and Sirignano that follows the d-squared law and can be generalized to include other more complicated scenarios as well. Is that the evaporation is controlled by this Spalding mass transfer number, which depends on the temperature and the vapor pressure of what's being evaporated away. These are just a series of coupled differential equations that can be solved numerically. In terms of validation of that series of coupled differential equations, I actually did some experiments in Bristol with optical tweezers, and I was very happy about this actually. The circles on the right here are the experimental values for an experiment where I had a droplet that contained water and salt evaporating to equilibrate to a new relative humidity. And then my simulated radius for that using those equations is actually this black line running along through here. So I was quite happy with that. In terms of the light scattering, there are 3 regimes of light scattering that exists that we care about. If particles are very small compared to the wavelength of light, they follow an intensity that goes as d to the 6, that's Rayleigh scattering. If they are very big, I didn't even put this in, it's considered optical scattering, and you can use equations that follow through with that. If they are on the order of the wavelength of light, that me scattering, they go as d squared. And anything in between, it's a blend that goes in between d to the 6 and d squared. And of course, to make our lives difficult, we'll write in this blend region, which means that we need to use the full equations. No matter, we can use these equations and the model has been taken care of. The idea is you put all of these models through in sequence, and then you obtain a post-evaporation droplet distribution. You convolve this post-evaporation droplet distribution with a me scattering distribution that tells you for a given droplet diameter how much light do you expect it to scatter. And finally, that gives you a sort of total light scattering intensity that you expect for your particular distribution that gets out at the end. If you do this for different concentrations, you can get a signal versus concentration plot. And I wanted to compare this with real experiment. So I used the actual machine, the LSD, and I did a bunch of experiments using a bunch of different conditions like temperatures and injection volumes and compounds. And you get data that looks a bit like this. So this is actually using the device. In terms of what responses you get, I found that there were 3 main types of responses. If you used a non-volatile compound, a semi-volatile compound like caffeine, and a up here. With the volatile compound, you can tell that if you increase the temperature, the signal goes down because it's volatile, it disappears, it doesn't make it to the detector. Semi-volatile, more interesting. What happens is, if we follow them through, this is the 25-degree line, and it sort of starts to increase as you increase the temperature. The signal intensity, that is, the signal intensity starts to increase as you increase the temperature. You reach a zenith, you reach a peak, and then it starts to drop off again as it starts to become more volatile, which is this sort of behavior that is put down here. So it reaches a peak and then comes back down with temperature. With non-volatile, it's actually just sort of the first part of this diagram. You can think of it as like that. So it increases with temperature. And again, with volatile, it's sort of the second half of the semi-volatile, so it only goes down with temperature. In terms of the gas flow rate and the role that plays, between 1 and 1.5, there wasn't very much difference, but then it's basically a dilution effect. As you increase the gas flow rate, you have a less concentrated plume, which means that less stuff goes through the probe volume and they don't get detected. Comparing this with experiment and my simulations, experiments are at the top, simulations at the bottom, and I get a qualitative agreement that's fair. When I expect volatile stuff, it disappears. Semi-volatile stuff, it does tend to disappear as I increase the temperature fairly well. And with non-volatile stuff, I get plots that basically line up on top of each other, which is again what I would expect. I did some CFD results to basically find out how the airflow inside of the ELSD was changing given certain boundary conditions. I did this with and without some additional restrictions that the actual machine has. So this was the empty chassis. This is the more realistic version of the chassis with all the different nooks and crannies put in. And this basically allows me to have a velocity and pressure profile that I can work with for the machine at each point that I can feed into my model later on. So in summary, I've started to make a working model that includes all of the different stages of the ELSD. I've built a database of experiments with different compounds, different volatilities. I've tried to validate that as best as I can, and I've started work on computational fluid dynamics to try and validate all of these things together. My next steps are to continue the validation process, possibly with some velocimetry results, possibly hot wire anemometry, and also try and validate those post-evaporation diameters by using maybe the AAC, which has been talked about by combustion, the DMA or the CPMA, and trying to expand my zero-dimensional model as well, try and make it more realistic. Thank you very much. Any questions?